You know, it's pretty amazing when you think about it. One of the single biggest challenges for today's most powerful AI is something we do without a second thought. Just understanding the difference between before and after. For huge models like transformers, that concept of order, of sequence, it just isn't built in. For years, the solutions have been really clever, but totally separate, like two different schools of thought that never talk to each other. Well, today, we're diving into the breakthrough that might just unite them all. All right, let's get right to the heart of it. The dog bit the man versus the man but the dog. We're using the exact same words, but the meaning is wildly different, right? One is a normal event. The other, well, that's a headline. For us, the sequence is everything. But for an AI, this simple example shows you the core of the position problem. How do you actually teach a machine mathematically that the order of things is the meaning? So the real issue here is that these incredible architectures, like the transformer, are naturally something called permutation-invariant. Now that's a fancy term, but all it really means is that without some extra help, the model has absolutely no idea what order the words came in. To a raw transformer, a sentence can look like just a bag of jumbled up words. To fix this, researchers came up with positional encodings, which are basically special signals they inject to give the model a sense of order. And for a long time, two brilliant but totally different philosophies have really dominated the field. First up, you've got RoPE. You can think of RoPE like a compass. It encodes an item's position by rotating its data in a complex, high-dimensional space. Then you have ALiBi. ALiBi works more like a ruler, adding a penalty based on how far apart two words are. Both of them work great, but they seem to come from completely different universes, philosophically speaking. And when you have two different solutions like that, it naturally leads to a massive scientific question. Are these just two clever hacks that happen to work? Or is there a deeper, unified theory that could actually explain both the compass and the ruler? A single, elegant principle that could govern how all AI perceives position. And that is precisely what this new research introduces. They call it GRAPE, and it's a new framework that does something way more profound than just giving us another method. It creates a single, principled design space that elegantly brings together the existing approaches, showing they weren't so different after all.
Now, the foundation for this amazing unification is a beautiful area of math called group theory. Don't worry, you don't need a PhD to get this. The easiest way to think about it is as a consistent set of rules for transformations, like rotating something or shifting it. It's like finding the laws of physics that say how data can be moved around in a really predictable, structured way.
So GRAPE uses this mathematical physics to show that you can build positional encodings in two primary ways. And here's the big reveal, the crucial insight. It proves that these two ways aren't competing ideas at all. They're actually two sides of the very same coin, and they both come from the exact same mathematical first principles. So what are these two families? Well, on one side, we have multiplicative GRAPE. This is all about rotations, just like our compass analogy for RoPE. On the other side, there's additive GRAPE, which is based on adding biases or shifting things around, just like the ruler analogy for ALiBi. The incredible takeaway here is that one single, elegant theory is responsible for generating both. Let's take a closer look at that first family, multiplicative GRAPE. This whole side of the framework is about using smart, norm-preserving rotations to encode position. Now, norm is just a technical term for the length or magnitude of a vector. By preserving it, the model can understand the order of words without accidentally making some seem more or less important than others, which is absolutely critical for stable training. It all happens in a pure mathematical space of rotations, which, as we just said, preserves the importance of each word. This is awesome because it guarantees that the connection between any two words depends only on how far apart they are, not where they happen to sit in the sentence. You essentially get all the benefits of RoPE, but now it's inside a much more general and powerful framework. And here it is. The proof is right in this quote from the paper. GRAPE doesn't just look like RoPE. Under a very specific set of conditions, it literally becomes RoPE. This is a huge deal. It means RoPE isn't some separate, competing idea. It's actually just one specific recipe from the much larger GRAPE cookbook. Okay, let's jump over to the other side of the family, additive GRAPE. This is the ruler's side of the theory. What it does is create a rigorous mathematical foundation for methods like ALiBi, which work by just adding a penalty based on distance. It shows this isn't just some simple trick, it's a deeply principled approach that comes from that very same group theory. So how does it actually work? Well, it's a really clever three-step process. First, it temporarily projects the data into a higher dimension. Second,
it applies a special kind of shift or shear transformation while it's up there. And third, this is the magic part. When it brings the data back down, that whole complex action just looks like a simple linear bias, exactly the kind of penalty ALiBi uses.
And once again, we get this powerful confirmation straight from the paper. Just like it did with RoPE, this shows that GRAPE's additive family can fully recover both ALiBi and another similar method called FOX as exact special cases. It just unifies that entire field of additive methods under one clean, theoretical roof.
So, the theory is beautiful, it's elegant, it's unifying, but this is applied AI, right? So at the end of the day, we have to ask the single most important question. Does it actually perform any better? When you build a model on this unified theory, what actually happens? Let's take a look at the results.
Okay, this chart shows the training loss for some large models. And remember, lower is always better. Notice RoPE over there on the left? Its loss is a little higher, and you can even see those little spikes, which tell us there's some training instability. The additive methods, ALiBi and FOX, they're better and way more stable. But then look at the bar for GRAPE. It consistently gets the lowest loss, and it's rock-solid stable the whole way through. So it trains better. But what about the final performance on actual tasks? This table lays it out pretty clearly. We're looking at the average score across a bunch of different benchmarks. RoPE kind of sets our baseline. ALiBi and FOX are a solid improvement on top of that. But right there at the top, that's GRAPE BAP, which is a specific version of Additive GRAPE. Let's just zero in on that winning number, 56.91. This is not just a theoretical victory, folks. The elegance of this unified framework translates directly into state-of-the-art practical results. It turns out that when you start from a more fundamental and principled foundation, you just end up building something that performs better.
So why should we really care about this beyond a slightly higher score on a chart? Because GRAPE isn't just another positional encoding method to throw on the pile. It represents a fundamental shift in perspective. It gives us a unified language to describe what we were already doing, and maybe more importantly, it gives us a map to explore what could come next.
So let's just nail down the key takeaways. GRAPE gives us a single theory that explains two major, seemingly separate approaches, proving they're just special cases of a broader idea. This opens up a principled design space, a new playground for researchers to invent even better methods. And as we just saw, it already delivers best-in-class performance and stability right out of the box. Which leaves us with a final, really fascinating thought. This work took two different successful ideas and found the single, elegant theory that connected them both. So the real question is, if we've now managed to unify how AI understands something as fundamental as position, what other core concepts in AI are just out there waiting for their own unifying theory?